Hey guys, welcome back to my channel, and this is Varun Tahin. So previously we have talked a lot about vectors and vector spaces and saw some common operations on vectors including dot products and some other algebraic operations. And now is the time to introduce ourselves to matrix and some specific operations on them like multiplication, transpose, inverse and linear transformation. So without further ado, let's start with what matrices are, its properties and where they are used. So you might be wondering, what is a matrix? So a matrix is a rectangular array of tables of numbers, symbols or expressions arranged in rows and columns in mathematics. So we have been given an example where this represents a matrix, where it particularly represents a table of 2 rows and 2 columns, and hence it is a 2 into 2 matrix. So the difference between a vector and a matrix is actually that vector is array of numbers with a single index, whereas matrix is a rectangular array of numbers with 2 indices as rows and columns. Also, vector is a way to simplify three-dimensional figures in geometry, whereas matrix is used in linear algebra for linear transformations. We will look at more differentiation between matrix and vectors by common parameters in later segments. But for now, you can remember that matrix is kind of an extension towards vectors. Okay, so like vectors or any other element in mathematics, it also has some properties in it. So the first one is commutative property, which does not hold true for matrix, unlike for vectors it does. Okay, so when we multiply two matrices, that is A and B, its multiplication is always not equal to the multiplication value of B into A. The second is associative property, which exactly holds true for matrix also. That is, when two matrices A and B are multiplied and its value is multiplied by C, that value is exactly equal to the value of A multiplied by value of B into C. Then third is distributive property, which is the multiplication of A into B plus C will always be equal to AB plus AC. And then comes multiplicative identity property, wherein A is multiplied by identity matrix will always result in A. Then the fifth property is dimension property, wherein if A's dimension is 2 into 3 and B's dimension is 3 into 4 matrix, then the resultant matrix which we will get after multiplication of A and B will always be 2 into 4, wherein we will chuck out the common dimension, which is the column number here and the row number here, and when they are equal, then we will neglect this and the resultant matrix will become 2 into 4 matrix. Got it? Then comes sixth property, which is multiplicative property of 0, wherein when A is multiplied by 0 matrix of the same dimension, then we will get the 0 matrix again. Now let's look at the differences between the vectors and matrices in terms of the parameters of comparison. So in terms of definition, vector is an array of numbers with elements enclosed in open brackets, but matrix is a rectangular array of elements or entities in a row and column vector enclosed in open brackets. Now a vector represents a magnitude and direction in its quantity with units, whereas a matrix represents the linear transformation and coefficients of the linear equations. In terms of index, vector has its elements in a single index, whereas matrix has its elements or entries in two indices denoted by various rows and columns. Now the fourth difference is that a vector is denoted in letters with an arrow on top of it to differentiate it from other quantities, whereas a matrix is denoted in uppercase letters. And lastly, a vector is used in simplifying the three-dimensional objects in geometry, whereas a matrix is used in linear algebra for linear transformation and forming linear equations. Now let's look at how two matrices are multiplied. So let's say that matrix A has a dimension of A1 and A2. That means A1 is the number of rows and A2 are the number of columns. Now when A is multiplied by B, which has a dimension of B1, B2, that is B1 is the number of rows and B2 are the number of columns, then they can only be multiplied and the resultant matrix AB can exist if A2 is equals to B1. Got it, guys? So as we have discussed previously also, that the number of columns of the first matrix should always be equal to the number of rows of the second matrix in order to multiply both of them together. And as you know that AB is not equals to BA, therefore for BA to exist, B2 should be equal to A1. And if this is true, then the resultant matrix BA will have a dimension of B1, A2. Now let's understand understand multiplication through an example. Let's say that A is of a dimension 2 into 2 and B is another matrix which is multiplied to A which has a dimension of 2 into 3. Now in order to multiply them together, we have to take individual rows of A and multiply them with the individual columns of B. Okay, so what we'll do is we will take first row which is 1 and 2 and multiply them with the first column of B which is 1 and 4. So 1 into 1 plus 2 into 4. So this is how it is done, guys. We have to multiply each of the element of the first row with each of the element of the first column, okay, like this, and then add them together. Now this way we will get 3 columns because this row is again multiplied to the second column, that is 1 into 2 plus 2 into 5, and then to the third column as well. So 1 into 3 plus 2 into 6. Okay, so this is about the first row. Now going to the second row of the first matrix, we will multiply this row by again the columns of B. So the first element of the second row will become 3 into 1 plus 4 into 4, and likewise for the other rows 3 into 2 plus 4 into 5 and 3 into 3 plus 4 into 6, and you will notice that we will get a resultant matrix of 2 into 3. Now let's move on to another concept which is transpose of a matrix. Now transpose of a matrix is nothing but changing the rows to number of columns and vice versa. Okay, so for this matrix A, which represents a 3 into 2 dimensional matrix, when we take a transpose of it, it will become a 2 into 3 matrix where all the rows will be changed to the columns. So you can see that 7 0 2 3 and minus 1 4 are changed as columns here. Okay, so therefore the transpose of M into N matrix will be a matrix of dimension N into M. Okay, and the value present at ij location in the original matrix will be present in the ji position of the new matrix. Okay, and we can implement this in Python. So let's say that we have a matrix A which is represented by 1 3 2 and 0, which is a 2 into 2 matrix. Therefore transpose of A will become 1 2 3 and 0. Okay, and this will be implemented by the NumPy library, and we can simply say np array to form the matrix, and then to take its transpose we will do dot t as a method. Now let's learn what is an identity matrix and afterwards the matrix inverse. Okay, so an identity matrix is a square matrix in which all the elements of the principal diagonal are ones and all other elements are zeros. Okay, so a square matrix you can regard where the number of rows are equal to the number of columns. Okay, so ideally number of rows are equal to the number of columns, and this is called as a squared matrix. Okay, so by definition you can see an example of identity matrix where the diagonal elements are all ones and the rest of the elements are zeros. Okay, so this represents a 2 into 2 identity matrix. If it was a 3 into 3, let me show you how it will look like. So it will look like something like this. Okay, and it has its property wherein if you multiply any matrix by this identity matrix, you will get the same matrix again. Okay, so this is about identity matrix. Now what is matrix inverse? So an inverse of a matrix A is represented by A with a symbol of -1 over here on top. Okay, wherein if the matrix A is multiplied by its inverse, we will get the identity matrix. And in Python you can directly derive the matrix inverse by the linear algebra dot inverse method of NumPy by supplying the matrix inside the method. Now let us understand what linear transformation means. So transformation by definition is ordered to move around the space and that the grid lines remain parallel and evenly spaced and the origin remains fixed. Okay, now a linear transformation is a function from one vector space to another that respects the underlying linear structure of each vector space, and therefore it is also known as linear operator or a map. Linear transformation are basically useful because they preserve the structure of a vector space. So many qualitative assessment of a vector space, that is domain of a linear transformation, may under certain condition automatically hold in the image of linear transformation. Now two examples of linear transformation can be rotation around the origin and reflections along a line through the origin, and this is how it is done. Okay, let's say that we change the basis vectors from 1 comma 0 and 0 comma 1 to 1 comma -2 and 3 comma 0. Okay, so this will represent the I hat and j hat, which are the basis vectors, and we try and multiply those. So when we multiply them and add them together, we'll get a 2 into 2 matrix where the basis vectors will be changed. Okay, and the new basis vector will be pointing to 3 comma minus 2 and 2 comma minus 1. So this has changed the space of the vector, and therefore transformation has happened. And as you can see down below, that there is a general formula wherein the previous vectors were I and j, and we had multiplied that by a vector represented by x comma y. Now while we multiply this, we will get the new matrix which will represent the transformed coordinates. And there is another example below wherein you can see the basis vectors which were previously 1 comma 0 and 0 comma minus 1 have been changed to 2 comma 0 and 0 comma 1. So therefore the column vectors will represent the new I hat and j hat and is represented with capital L. Also the new vector point will be represented in terms of this L multiplied by the original vector. Now like other operations, linear transformation also has some properties associated with it. Okay, so if we are defining L by the linear transformation and V and W are the vectors, then linear transformation also supports additivity or distributivity as one of its properties, wherein if we add the two vectors L and W and multiply it by L, then the result will be same as multiplying L by V plus L by W. Also homogeneity and associativity hold true in this case, where if we multiply a scalar quantity by a vector quantity and then multiply the linear transformation with this value, it will be equal to saying that we directly applied linear transformation on the vector and had multiplied it by a scalar quantity. Now there can be a single transformation or a composition of various transformation at one go also. Okay, so this is a matrix for the transformation called as shear. Okay, we will see that in the later segment, but just remember that this represents a kind of transformation which is shearing. Okay, then if we multiply this by the rotational transformation, which is 0, 1, minus 1 and 0, and multiply it by a vector, let's say x and y, okay, where this represents A, this whole represents B, then this will be equivalent of saying that multiply 1, minus 1, 1, 0 by x and y, okay, where this will represent the composition, okay, which is C. So what this will do, this will have the properties of both shearing and rotating the vector. Okay, so hence this will become a composite transformation matrix. Now this is the example of a visible transformation called as shearing, which we were talking about earlier. Okay, so this is basically doing a shearing of a rectangle to make it parallelogram, where the original points were depicted by these purple colors. So 0 comma 0, 0 comma 1, 2 comma 1 and 2 comma 0, and you can see while applying the shearing, that is this matrix, which is a transformation matrix for shearing, you will get the resultant parallelogram with the new coordinates of 1 comma 1 and 3 comma 1. So that will be all for today, guys. We will look at more concepts in mathematics relating to matrices in the upcoming session, so please stay tuned by clicking on the bell icon so that you don't miss any updates. Also please subscribe to my channel if you have not yet done already, and if you want to stay updated on the latest content on data science. I'm giving my best to cover every topic from basics so that this course appeals more to newcomers in this field. We'll be looking forward to meet you all in the next session. Until then, thanks, take care and happy learning.